Welcome, everyone. Today we'll see a brief introduction to artificial intelligence along with its history. So just a reminder of what we've mentioned previously, that in our civilization we've had mainly three revolutions: agricultural dealing with the control of matter, industrial dealing with the control of energy, and information dealing with the control of information. And of course, this is relevant for the study of intelligence because there's a big question: what is intelligence? And this is still an open question. And it's not a recent question since antiquity. People have wondered, perhaps with different words, like what is the soul, what is the mind, and some people basically try to define intelligence as that it made us different from other animals. So of course that was an anthropocentric definition, and we could try to find a definition like, okay, I don't know how to define it, but I know it when I see it, but that's not very useful to study intelligence, to understand it, and to build intelligent systems. Scott Fitzgerald wrote that intelligence occurs when we have at the same time two contradictory thoughts. One proof of that is that mankind knows that it's lost, still it does everything it can to save itself. Actually, this quote from Fitzgerald, when it comes from the humanities, will be useful, as you will see later, when trying to explain the limits of artificial intelligence. So basically, for Fitzgerald, intelligence basically a logical contradiction, and artificial intelligence is based on formal systems that cannot handle contradictions properly. Another definition of intelligence from one of my classmates from university, Prof, the art of getting away with it. So kind of gives us an insight, but perhaps the most useful I heard from Dr. Mario Lagunes, who actually met Claude Shannon and Norbert Wiener and many others. And he said that in order for something to be judged intelligent, that something needs to perform an action or a behavior, and then a third person or a external judge needs to decide whether that action or that behavior was intelligent or not. So that kind of satisfies and solves many problems, but of course it's subjective. It depends on the judgment of the judge or the observer. And in some cases, the same behavior might be considered intelligent or not. But of course, better than nothing. So perhaps we can't agree on what intelligence is, but most of us would agree that it deals with information processing. So it's not a coincidence that the development of artificial intelligence began with the information revolution. You will see a bit of the history right now. But it was only when we were able to have enough storage, and nowadays with big data, that we can study, simulate, and improve cognitive processes. So there are stories of artificial creatures since antiquity. So in Chinese mythologies, in Greek mythologies, in Mayan mythologies, in the Greek, Jewish, Arab, there are lots of examples of artificial creatures. So Pygmalion, Galatea was a sculpture and fell in love with his creation. And I remember properly, the gods made her alive. I don't remember precisely the story and what happened afterwards, but the thing is that she was an artificial creature. Similarly, the golem from Jewish folklore, it's an artificial creature, so it's a bit like man playing God. and the problems that might arise from such endeavors. But we already mentioned that with the development of clockmaking, different automata were developed. So that's a production of Parkinson's dog, which was able to eat, digest, and defecate. So it's like a expensive mechanical toy. There were also some music playing dolls of Dross, and then angry mob in Spain destroyed them because they considered that he was playing God, and that was a sin. And I mean, still was Inquisition active in those years, 18th century, as it was. So robots, as we know them, actually the term robot was proposed by Karl Čapek a bit more than 100 years ago for his theater play RUR, and comes from the Slavic word that means to work. It's like artificial workers, and they, from science fiction, they capture the imagination of many people, and they have been developed, and now, let's say, they have become not yet prevalent, but they have Roombas at home, and there are robots in industrial settings and in many other settings. We already have robots in everyday life. So in the 1950, Turing published his paper, What is Mind? Computing Mind. I forgot the name of the paper. About, well, some people say that it was the first paper about artificial intelligence. Still, the term wasn't coined. But he asks the question whether a machine can think. And he says, well, that's a very ambiguous question. So let's try to have an operational definition. And he proposed a test, which now is known as the Turing Test, which is based on the imitation game. So the imitation game is such that you have a judge that communicates with two people, a man and a woman, and the man poses as the woman, and the woman she poses as herself. So the judge needs to decide who's the man, who's the woman, and the man tries to deceive the judge. The woman tries to help the judge make the right decision. So Turing changes the man for a computer, and he says that if the computer can fool a human judge more than half of the times, because, I mean, if it's just random, then you would assume that half of the time the computer would fool the human just by chance. If it's better than chance, then you can say that it's intelligent. And of course, this has limitations, and actually, already for a few decades, there have been Turing tests organized, and they invite people to submit their programs to try to pass the Turing test. And this has been that worked. And actually, early on, some programs passed the Turing test, but basically, they will introduce some typing errors. Then the naive judge would say, "Oh, computers don't make mistakes. That should be the human." But so the computer was passing the Turing test not by being as smart as a human, but being as dumb as a human. And say that's not the purpose of the Turing test. Yeah, so it's something like this. And then there have been extensions of this. So, for example, one can say that the Turing test is specifically for conversation, but then you could say that playing chess, it's a completely different test. So you can say that Deep Blue kind of passed the Turing test for when it beat Kasparov, and then we've had other computers that perform better than humans in many other domains and games, but there's still plenty that they are very far from beating humans or having a human level performance, and it's uncertain whether they will ever be. And moreover, computers are not generalists in the sense that, let's say, Deep Blue can beat you at chess, but it won't beat you at, I don't know, tennis. A completely different problem. Or autonomous car could drive on average better than humans, but it won't be able to drive a motorcycle. It's a different set of skills. But you need a different program. So this is why some people have tried to reach what is known as artificial general intelligence, but so far they've produced only, no concrete results so far. And actually, the CAPTCHAs that we are forced to fill every now and then to show that we are human, it's like an inverse Turing test. So we are trying to convince the computer that we are humans and not a bot trying to enter the system and get some data or do some function. So it's the same idea, but inverted. So the term artificial intelligence was coined in 1956 over the summer in Dartmouth College in New Hampshire. Many people met, and there were different lectures. So we have already spoke about Claude Shannon. Robert Simon later won a Nobel Prize in economics. Julian Bigelow was co-author with Turing and Rosenbluth of his 1943 paper on behavior, purpose, and teleology. And Bigelow later was working with Jean von Neumann in Princeton to develop their computer that was before this, about Ashby, McCulloch of McCulloch and Pitt fame, the proposers of first model of neural networks. John Nash, if you watch the film A Beautiful Mind, it's about life. He developed game theory. So I mean, many bright minds of the age were there, and they established a program was developed over the next years, which involved automated reasoning, theorem proving, games, natural language processing, robot search problems, and first flavor of connectionism developed by Rosenblatt. However, he died and then kind of died out. He seems he didn't left people to follow in his footsteps. And I mean, it's not very different from the era that we have today in artificial intelligence, but they were promising that in 10 years or in 20 years we will have robots and they will have human level intelligence and they will be able to do this and that. And of course, after a few years that they didn't deliver, the funding was cut. So they entered what is known as the AI winter in the 1970s. Then, let's say, research continued. And in the 1980s, there was another wave with by personal computers. So, let's say, with much more people with access to computing power, there was a renewed interest in artificial intelligence. Expert systems were developed. There was also knowledge representation, a second wave of connectionism, pushed by Hopfield and the new algorithm, like the backpropagation algorithm, which was shown to solve different pattern recognition problems. So say lots of applications, neural networks. But again, it promised too much. And in the 1990s, there was a second winter. And it's not that it stopped, but again, they promised too much and they didn't deliver. So the funding was cut. But then already in the 20th century, there were new advances related to machine learning, deep neural networks, and there have been massive investments. So for example, A few years ago, China announced that they would invest, I think, $100 billion in the next 10 years to develop AI. So founding institutes and research and startups. And their goal was to be the world leader in AI by 2030. I think they will reach that goal much earlier because no one else is investing so much. I think it was 2 years ago. And Trump announced, oh yeah, we will also invest in AI. He will say how much, when, and let's say. Just a comparison, in the United States, a big investment was a donation given to MIT of $100 million. So it's like 1,000 times less than China is investing. And also Russia attempts to make investments in artificial intelligence. And the promise is that since this technology, in principle, we can develop relatively fast, then you don't need to wait years for, say, crops to grow. If you're going to invest in agriculture or energy, let's say the returns of investment are very long, and in general, in information technologies, the returns can be very short term. So it's convenient for different countries to make investments in this area. And also, we've had, let's say, a much broader application of AI in our everyday life. So we have recommendation systems like in Amazon or Netflix or Tinder, or almost everywhere where we're interacting with a huge database system. Then there are algorithms that helps us say, personalize our choices. There's also, there has been huge advances in language recognition, pattern recognition, image recognition, also related to entertainment industry. I mean, it has permeated to our society. And let's say that's more or less where we are. Question is whether we will enter another winter or not, but we'll speculate about the future at the end. So one of the advantages that the development of artificial intelligence has had over decades is that what is known as the synthetic method. Traditionally in science, we use the analytic method, which involves you have an idea or a theory, then you make an observation, you get some data of that observation, and then you contrast the data with your theory, and that validates or falsifies your theory. And usually it falsifies because say our theories are not necessarily right, and then you refine the theory until it's more or less robust. And with the synthetic method, an alternative is to observe a phenomenon and then build a model of that phenomenon, be a robot or a software simulation. Then you observe the simulation for the robot, and then you contrast that behavior to what that was the phenomenon, and then you adjust your theory. So, of course, this does not necessarily prove. So, for example, let's assume that we observe a little mouse, and then we build a robot mouse, and they behave in a similar way. Doesn't mean that the mechanisms that we build for the mouse are the same, for the robot mouse are the same as for the biological mouse. It means that we are getting a better grasp about the requirements for solving that sort of problems. So an analogy in mathematics is that you can have infinite number of functions that can fit a data set with an arbitrary degree of precision. So how do you know that the function that you're using is the real one? So, I mean, you don't, but it gives you an idea because it tells you more or less how many dimensions you require to fit that data, what are the potential dynamics of such a system, and so on. So with artificial intelligence, we're able also to understand biological intelligence, and with that understanding, build artificial systems that exhibit similar properties. And then by building those, we can also increase our understanding of biological intelligence. So this also known like from biology to engineering and back. And this has been applied in cognitive sciences. So this like a huge umbrella for AI, psychology, linguistics, philosophy, artificial life, sociology, and so on that deal with cognition. And I mean, this arose a bit later than artificial intelligence, and not only includes artificial intelligence, as I mentioned, it's a bit broader. And in some cases, it's more philosophical, but it's kind of grounded philosophy because, let's say, well, you have a bit of everything. And for example, people have noticed the relevance of the body for the mind, so it's known as the embodied mind. So depending on the physical hardware or the physical body of an organism, their information processing that they need to make can vary a lot. So there have been some experiments by varying in robots the position of the sensors, or better, when the sensors can be moved, then the solutions that the robots find can be much more adaptable than if the sensors are fixed. And you can imagine that depending on where the sensors, your solution, or let's say the controller for a robot, should be very different. So let's say the body, let's say it's an essential aspect of intelligence. So many of the initial and actually still some current attempts for artificial intelligence are equivalent to a brain in a vat. So it's like some intelligence that is isolated and just communicates through inputs and outputs. But basically, it's the idea that also in our bodies, our mind is in the brain. But for many, well, for a few problems, this is good enough. But for many situations, especially those that deal with interaction with the real world, the body is part of the solution, and you cannot really separate body from the mind. So, I mean, this is an ongoing field of research. And this is related also to the embedded mind, meaning that the body is in an environment. And if you don't take into consideration the environment, it's a similar argument to embodied mind, but with environment, that in many cases, the information processing that we would call the mind takes place through the environment, as we saw with ant colony communication. There's stigmergy, which is communication through pheromones, and this part of the cognitive processing. And this, if we push this further, we can go to speak about an extended mind. This notion was proposed by Andy Clark and David Chalmers about 25 years ago. And the idea is that, say, we have many tools that we use for our information processing. So they use an example of a person with memory problems, and he has a notebook, and then he writes things in his notebook, say, so that he remembers things that we would normally store somewhere in our brain. So what they were proposing is that we should consider this notebook as part of his mind, even when it's not part of his brain, because it serves the same function. And of course, it depends on whether you have a perspective that focuses on function or substrate. If you are concerned about the substrate, then you just focus on the brain, and then you consider the body and the environment as inputs and outputs. So Andy Clark has an influential book, but he has several influential books, but perhaps where he first posed all these ideas is called Being There, putting mind, body, and brain together again. So that's highly recommended. And there's a typo here. It's not inactive, but inactive mind with an E. So this was actually proposed in part by Francisco Varela, the 1990s, where with Evan Thompson and others. And they were noticing that the mind, or what we call mind, it's a constant process of action. So we cannot really separate, like, oh, we have inputs and outputs, and then here is the mind doing some processing. But we need to take into consideration the constant loop of the mind interacting with its environment, with the body, and this cannot be separate. And it's relevant for adaptive computing because precisely the idea of an inactive mind requires that the computing or the information processing that such a mind is carrying out will not be predetermined, and it has to adapt constantly to the changes in the environment. So I mean, that's why I'm bringing this up here. So yeah, I mean, there are many open questions in artificial intelligence and in cognitive science. And many people wonder whether this technology might be harmful for a species. In recent years, people like Stephen Hawking and Bill Gates and Elon Musk and others worried that we should restrict the development of artificial intelligence. And of course, this is a problem not so much about the technology itself, but about how we use it. And I mean, the nuclear energy example is a paradigm for this. I mean, you can use nuclear energy to generate energy or to destroy things. So, but of course, we need to consider how we will use this technology in different contexts. I mean, governments are also, well, not only governments, but say it is being used already for weapons. So companies that are selling these weapons and the governments that are buying these weapons and using these weapons, I mean, they're already taking advantage of this technology. Of course, there are many ethical questions surrounding artificial intelligence, and these, of course, have to be discussed. So we can ask whether AI is good or bad for society. And again, it depends not so much on the technology, but on how we use it. And this will depend also on who is controlling the data and the algorithms. So, and on how open or participative are our systems. So, if governments have control over data and algorithms, then you have to trust whether they're good governments or not, and the same for companies. And it seems that nowadays, well, the tendency is that the companies will be controlling all of this because companies can expand globally. Governments are limited in the sense that if a government develops their own, say, technology of AI and they ensure that it's beneficial and everything and open, they cannot replicate it to other countries. Companies can easily do that. And society lacks the capital and organizational abilities to demand companies to make these technologies open, available, and to say so that we have a say on what kind of technology they develop. So it seems very few individuals, private individuals, will be controlling all of this. So of course, this can be worrying, and there should be some regulation. But usually, that regulation comes only after we've had a few examples of things that go wrong. So let's hope that not much damage comes out from those things. Then that regulation comes quickly, and say we're able to avoid tragedies. But I mean, it's not possible to say to stop AI research because of the potential risks. Not only because there will always be people trying to develop it. Like, for example, with genetic engineering, there were moratoriums for different technologies like stem cell research or for say genetically engineering humans. But then some crazy guy in China, oh, I already did it, and of course there was a backlash from the international community. But I mean, even if we agree, okay, we shouldn't do this type of research in AI, very probably someone somewhere will do it. But not only that, we are, most of us will be gladly willing for this technology to continue because basically they allow us to make better decisions in theory, different skills, and also they make more efficient our systems. So, I mean, one example is with GPS. Google Maps or Waze, they make mistakes. They sometimes or often send us through back roads and the wrong part of the town. And I mean, because their algorithms don't consider several details or the maps are wrong, so they will send you through, say, unpaved roads or places where there are no roads. But we have become so dependent on this technology that even when we know that we shouldn't trust them, we keep on using it. So of course it's not perfect, but it's already better than we could be without them. So we keep on using this technology, and yeah, we can say, oh, it will be problematic to say lose our freedom of choice, but we gladly give that freedom because in many cases, or on average, the choice that algorithms are making is better than the one we do. So we delegate that freedom gladly. And it was similar discussion around privacy of information. Like, oh, do you agree to give us your information? And few people will say, no, I don't want to give you my information. But most of us would say, yeah, sure. Here, have all my information. Because I want the benefit, the service that you're offering. So as an anecdote, in 2014, I was part of the Mexico City team of the Audi Urban Future Awards. We were competing against Berlin, Seoul, Boston, and we won because we were trying to improve the mobility to Santa Fe, and we would ask people, oh, would you share your mobility information with us? And they have such painful commutes that they will gladly, yes, here, have all my information and have my credit profile. Not so much, but they will gladly share their information because they see that they're suffering so much that even the possibility of reducing for a few minutes their commute, it's worth it. So in a similar way, if you can get an advantage from sharing your information or delegating decision making, we gladly go that way. So just as a parenthesis, in Mexico, the first computer arrived here at UNAM 1958, so it was already after the Dartmouth conference. And probably it was until 68 that the first researchers that had learned artificial intelligence in the United States and Germany, Negrete, and Guzman Arenas was a student of Marvin Minsky at MIT. They returned to Mexico and they started their own research groups. Negrete here at the Biomedical Research Institute, Guzman Arenas in the Polytechnic Institute. 1994, the Mexican Society of Artificial Intelligence was founded, and a couple of years ago, we finished the national agenda of artificial intelligence. So, I mean, we could say that we are way delayed compared to other countries like China, United States, and Japan. But I mean, compared with other Latin American countries, we're not so bad. We're similar to Argentina, Brazil, Chile, Colombia. A bit better in some cases. But yeah, I mean, there's a huge potential to invest more in artificial intelligence. The beginning of this government, there was some talk about converting Infotech, which is a CONACYT center for information science that they wanted to shut down, and they were thinking about, okay, let's not shut it down, but transform it into an AI center. I think not much has come out of it. But yeah, I mean, let me just share just a couple of case studies that we've worked with. So one has to do with detecting tax evasion using AI and network science. So 2 years ago, we got a huge data set from the SAT. That's the Mexican equivalent of the IRS. And so in their data set, there are more than 80 million taxpayers, including people known as physical persons and companies known as moral persons. And they basically meet invoices to each other. So with those invoices, we can build a network of who meets an invoice to whom. So that's a directed network. And it can be multi-layer network because we had it for 4 years, month by month. What was the aggregate invoice between two taxpayers, either physical or moral. And so the data set was like 7 billion transactions, or let's say aggregated invoices for 4 years. So we could build the networks either month by month or year by year or for the whole time. And they also gave us a list of with less than 10,000 tax evaders that basically they fabricate invoices so that their clients can deduce those taxes. So let's say I have a company and I should pay $1 million in taxes, but I don't want to pay those taxes. I want to evade them. So I go to one of these tax evading companies. They will give me an invoice for that $1 million. Then I can deduce that tax and kind of give them a commission and keep the rest. So that's quite a common practice in Mexico and in other countries as well. And that's just one mode of tax evasion. There are others, but we were focusing on this. So we basically, with their small data set, because you are comparing like, okay, we have less than 10,000 taxpayers that are already identified as tax evaders in a universe of 81 million. So it's highly unbalanced. And we wanted to get like a list of taxpayers that were not tax evaders for sure, but the SAT told that they couldn't give us such a list because they cannot say, oh yeah, this person is not a tax evader. They can tell, okay, this is evading taxes, but they cannot say whether someone is not evading taxes. But anyway, we combine different methods, deep neural networks, random forests, and also network science to identify potential tax evaders. And we gave the SAT a list of, I don't know, about close to 50,000 taxpayers that were highly likely to be tax evaders. So you can sort them by how much money they should have paid. And then humans were following this. So we got anonymized data, so we didn't know which companies were these. And but soon after, many big companies started to pay their taxes that they somehow hadn't paid in a few years, in recent years. So for example, here you can see that there are lots of people that get invoices. Here the red ones are the tax evaders that are already identified. So this one gave invoices to all these people, but this one also gave invoices to these people. So this is a suspicious now, but most probably it's part of the same organization because it's relatively easy to get a new company and start making invoices for some time, and then you close that company and you open another company to make invoices. But here, if you have the same clients and you already know that this guy is a tax evader for these people, then you can identify people who are also giving, let's say, taxpayers who are also giving invoices to this, and very probably it will also be a tax evader. In another project, we use this for wind speed forecasting. I mean, this is useful for wind generation. I mean, there are many applications. And we can ask ourselves which method is best. And in 95, 97, Wolpert and McCready published papers about free launch theorems for optimization and search. And basically, what they prove is that if you consider all possible search spaces, then there's no search method that is better than random search. And I think I mentioned this already in some class that this phrase over all possible search spaces, actually, most of all those possible search spaces are very random. So then it makes sense that random search would be as good as any. However, in reality, most search spaces are not random. They have certain structure. But the importance of these theorems is that different structures are best explored by different search methods. So, yeah, I mean, because of this, there is no best search method, and then you can generalize this for artificial intelligence, because you can also see artificial intelligence as a problem of search. There's a book by Keith Dawson, Keith Downing, Intelligence Emerging, and he sees precisely most of artificial intelligence research under an umbrella of search. So for the future, maybe there could be another winter. Maybe, but not in the next few years because of so much investment that is being done already. And actually, even when many of the promises that were made have not been delivered, like autonomous vehicles, that they were a few years ago, like, okay, in 2-3 years, we'll have already autonomous vehicles everywhere. I mean, we do have autonomous vehicles like Waymo, the Alphabet company in Arizona, and it's like Uber, but with autonomous vehicles. But they haven't managed to scale it up for different reasons. So, I mean, we do have autonomous vehicles, but they are not everywhere. And with many technologies, it happens that a technology is developed, but because of its cost or some other reasons, it's not massively adopted until decades later. So, for example, polarized glasses, they were developed in the 1950s, but they were very expensive. So, for example, in the futuristic shorts, the 1950s, they were showing like I think the windows of airplanes that they would be polarized, but it was way too expensive, and it was only I think the Boeing 787 that have this technology. You press a button and then they come out. So there's always the question of new technologies, whether there would be some layoffs, that they would replace people who were doing the tasks that computers are taking over, and I mean, in the Industrial Revolution, that was the same issue. And yeah, I mean, very probably this will occur, but at the same time, there are new niches and new opportunities for new jobs to arise. So, I mean, I don't think that artificial intelligence will lead to a massive unemployment, as some people might fear. And also, there might be new technologies that could be developed with AI. We don't know, but I mean, it's already transforming our society, and whether this transformation will accelerate or will stop, we don't know, because so for example, you might know about Moore's law. So Gordon Moore, one of the founders of Intel, noticed in the 1960s that the number of transistors in chips was doubling every 18 months or something like that. And he predicted that this trend would continue over the years, and not only it continued for about 5 decades, but it was actually a bit faster. So this led some people to speak about the so-called singularity. Well, actually, today I learned that actually Jean Paul Neumann made the same prediction in 1955. So he was helping develop the first digital computer, the ENIAC, in Philadelphia and at Penn State. And so by 1955, he told that since 1945, the speed of computers have doubled every year. So although if this continues, then we will achieve computational power very quickly, a very high computational power. So Moore formalized this properly, and this led some people to say, "Oh, we will reach a singularity, and then computers will take over, and we will be able to download our minds as computers." And I don't know what those, but this has several mistakes. One, an exponential increase does not lead to a singularity. I mean, it just keeps on growing faster and faster, but it never reaches infinite. I mean, the limit when an exponential function reaches infinite is at infinite. When x is infinite, then the exponential function of x will be infinite, not before. You will need a hyperbolic function for that, so that in a finite time you would have you will reach an infinite value. And this is not hyperbolic; it's exponential. So that's the first mistake, and that should be already sufficient to dismiss all this nonsense of singularity. Second reason for dismissing it is that these Moore-like laws that apply not only to processors but to storage and to the price of storing the price of computers has also been reducing exponentially. Another thing is that all this applies to hardware but not to software. So we are having indeed faster and faster computers. We're having faster and faster computers exponentially, but the software was not improving as fast as hardware. And there's a limit to the complexity of the software we're able to build. And automated software also has its limitations. So that's another limit. And the third reason, if the first were not enough, is that very common that you have an exponential process and then it saturates. So for example, bacteria growth is exponential. But then I don't know, if you make the calculations of how fast E. coli grows in a petri dish, if you continue exponentially, then I don't know in how much time they would be larger than the mass of the Earth, like in 3 days or something like that. But of course, there are limits, physical limits. Either they finish the sugar or whatever you're feeding them, or they cannot overflow the petri dish, and then the environment changes. So, I mean, there are limits, and I mean, many people have tried to impose these limits on Moore's law, but these have been overcome with new technologies. But I mean, there are physical limits in the sense that you cannot say go smaller than the atomic scale. Since that if you could harness electrons so that an electron could be codifying one bit or storing 1 bit, that's already very small. But then you cannot go smaller. And there are also limits about the clock speeds of processors. So you might have seen that the maybe that you were too young. So in the 1990s, say the processors were increasing their speed basically with faster clocks. So the 486 processors were, I don't know, 40 megahertz or 80 megahertz. Then the Pentium was, I don't know, 100 something megahertz and so on. It was faster and faster. But then they reached about 3 gigahertz. That's it. You cannot go much faster because just the metal melts. They generate too much heat. So actually, current processors, and also trying to save energy, I mean, for mobile devices, they have clock speeds, I don't know, between 1 and 2 gigahertz. And what they do nowadays is that they have like a lower clock speed, but then if the processing required, then they increase their clock speed and then they go down again. What people try to do is like, okay, we cannot increase the clock speed, so let's make multiple processors and multiple cores. But then to program this is not trivial. So in theory, you have more computing power because you have, say, at your disposal more cores and more processors. So some operations indeed can be made faster, but let's say classical programming is still linear, so that kind of flatlined already for 15, 20 years, the speed at which most programs that we make run. So yeah, no singularity. So some of the implications of artificial intelligence, as I mentioned, is that we are trusting machines more and more, and whether this will be beneficial or not, I guess it's difficult to generalize. It has benefits and risks and problems. On average, we can say that they make better decisions, or we will be able to make better decisions with support of artificial intelligence. Cesar Hidalgo and others have a interesting book called How Humans Judge Machines. So just before the pandemic, he was here at the C3. So if you search the C3 YouTube channel, you can hear his talk about that book, or you can download his book. I think it's available for free. And it's very interesting because I'm lying. And he spoke about economic complexity. But anyway. So they made lots of psychological tests. So basically, they were posing situations for people, and then people were evaluating these situations. So, for example, if there's a situation where there is the risk of a hurricane or a volcano, and there's the decision to be made where to evacuate the village or not. And then there's one scenario where humans make that decision, and another scenario where machine algorithm makes that decision. And of course, it's the wrong decision. They decide not to evacuate, and they should have evacuated, and many people died. So then the question for humans, for the participants, is how guilty, or say they measure this in a direct way, like, oh, would you hire this person algorithm again, or how responsible that person algorithm is, or I mean, with different questions, they kind of try to measure how harsh our reaction for that bad decision is. And in that case, it's interesting that we kind of tolerate the human error more. It's like, oh, well, yeah, it's, I mean, it's a weather event or a volcanic event. Yeah, the human made a bad decision, but yeah, humans make mistakes. And however, the computer should have known better, then it's very bad, bad computer. But then another situation, imagine that you have a robot at home doing the cleaning, and they grab a US flag and mop the floor with it. And let's say humans judge like, well, yeah, the robot doesn't know that the human flag, that the US flag is kind of, I mean, an important symbol, and that they shouldn't be desecrating it in such a way. So it's not a problem. We shouldn't leave the flag inside of the robot. But then if a human does that, like, oh, I'm going to clean the house and I grab the flag and mop the floor with it, then that's unforgivable. So it's interesting how for the same situation, the same mistakes, humans or machines are judged differently. But it seems we'll have more and more dependence on technology. The question of responsibility is important because, I mean, in the context of autonomous vehicles, this has been discussed widely that, for example, if, let's say, there's an accident or an autonomous vehicle runs over a pedestrian, who's responsible? The owner? The owner said, well, I wasn't driving. I mean, yes, it's my machine, but I didn't control it. So then, okay, who controlled it? The person who sold the car? No, they didn't build it. So who's responsible? Company that built the car, or the engineers, or the algorithm itself? So the responsibility kind of dilutes, and it's difficult to say, oh yeah, it was because of this person or this process that that person was run over. So that's a risk because let's say as we might be making better decisions, but these decisions are becoming distributed. So this also distributes the responsibility. And I mean, it's already happening even without artificial intelligence, like the accident in the Golden Line of the metro. The responsibility was also diluted because, say, who was responsible? The mayor, the supervisors, the director of the metro, the company, the contractors, the people who actually build it. They will say, oh no, I was just following orders, or oh no, I told them to do this and they didn't do it properly, or we didn't consider this and that. So there are many examples where you have similar tragedies, and then since there were so many people involved in a project, you cannot say like, oh, it was this guy's responsibility and they made a mistake. So it's like systemic failure. I mean, this is already happening even without artificial intelligence, but very probably it will happen more and more. I mean, we could say that AI will help us extend our mind. Maybe we'll be able to do things better. Maybe we'll have a cognitive increase. I don't know, maybe if we consider our extended mind, let's say us plus our technologies, but at the same time, if we depend more on our technologies, we'll be more stupid without our technologies, and then we'll become more dependent and we'll be capable and so on. Just like before mobile phones, we were able to memorize phones of our friends and family, and now we can't remember even our own phone because we depend on our technology to do so. And also, I think there will be a convergence in the sense that, I mean, already the human species, since its inception, is characterized by the use of technology. Language, fire, later writing, agriculture. So the technology is something that characterizes our species. And I mean, we're not the only species with technology, but we have developed most of our capabilities with technology. So, I mean, already, well, not already, but since antiquity, you could not separate a human from technology. And of course, this is becoming more and more difficult. So, and what I want to say is that technology is what makes us human already since thousands of years ago. So this technology will also be part of our humanity and very probably will define what it will mean to be human in the next centuries. So there are several questions: whether companies or governments dominate, whether individual, private, corporate, private, public. Already mentioned that it seems that companies seem to have the leading in this. How inclusive technology will be, because we can have the best technology, but only a few people have access to it. Then that might generate several problems. So we have to do wealth distribution and also how much we're willing to pay. But from what we've seen, let's say, since the cost of different technology is reducing constantly, because of economies of scale, it pays off companies to offer technology to everyone, or to as much people as possible, to say not that it's something exclusive. So, for example, with smartphones, the first generation, they were used by few people, or computers. But let's say the companies that make computers and phones benefit if everyone uses them. So let's say, doesn't mean that they will give them away for free, but there's a strong push so that everyone has access to them. So whether AI will lead to emancipation or slavery of our species, I mean, emancipation would be that something like an eudaimonia, where there's no suffering. Slavery, where basically we are so dependent on our technology that they do whatever that we do whatever they tell us, and a dystopic future that many films portray. And I think the future will not be in any of those extremes, but how much to each we will depend on the decisions we'll take. So just to conclude, we have a specialized program in Coursera, Introduction to Artificial Intelligence. So if you're interested, for UNAM students, it's for free. So yeah, we have about 8 courses, introductory courses in MOOCs, as open online courses with colleagues from IMAS. So yeah, you can check it out. Other questions? Oh, there is a chat. In the chat. Let me read. So Anayatin writes, so artificial intelligence and robotics technology is constantly advancing. Companies need to realize that their AI systems are not immune from hacking. So you should protect yourself against the possibility of your chatbots turning evil. For example, we're already seeing cases where hackers take control of bots and provide them with false information, for example, directing customers to a fraudulent website. Also, make sure you have adequate security technology and protection against threats to deal with this type of situation. I mean, many people worry about that. So, for example, autonomous vehicles, whether if they are hacked, then it could be highly problematic. But, I mean, this is a constant risk. There's an ancient Italian film, I can't remember the film because it's old, that I didn't watch it, I just heard it from my father. that there are some bank robbers, and the way they get away from the police is that they hack the traffic light system in Rome or somewhere else. So basically, they hack it in such a way that they are able to get away, and then they get red lights, the police that are chasing them, and that's how. So yeah. So yeah, I mean, similar risks arise. Well, in general, the thing is that the risks are increasing as our capabilities are increasing, in the sense that the risks from making mistakes 5,000 years ago, what would be the worst risk? I mean, simply by the amount of energy we could harness, let's say you couldn't affect, I don't know, maybe burn a few hectares or kill thousands of people in wars. But let's say with the capacity to harness energy, like nuclear energy, or to say all the things that we do that are affecting the planet, they're happening because, let's say, in order to be able to fly quickly all around the world, then we need to process fossil fuels, then these generate pollution and so on. So the more we increase our capabilities to control phenomena, the impact of our activities going wrong also increases. So yeah, that's something we should consider. So for example, we had a global system that controls, for example, autonomous vehicles. On the one hand, it could be very efficient, but then if it goes wrong, it would go wrong very badly, as it could have never been wrong, in the sense that if there's an accident, at most there would be some other cars crashing there. But if you have, or at least in one city, if you have all the vehicles controlled from the same system, if something wrong happens with that system, then in principle it will affect all vehicles in a city. And we've never had that risk, even if it's very small. So, yeah. Questions?
So we could measure how much artificial intelligence, how much useful it could be in a specific problem. I mean, if you take a society in, I don't know, Silicon Valley, they will accept anything, any artificial intelligence very quickly. But if you take the same thing and you put it from Africa, Latin America, we didn't accept it very quickly, or even that will gave us much problem that we don't understand. So
Yeah.
is there a measure?
Yes. I think you can have specific measures, not like a general one that will be applicable to all possible AI. But for a specific problem, yeah, you can say, okay, this is the performance or the delay or the cost without AI, and then you try, okay, this with AI, and then you say, okay, it improved this percentage. But this is also arbitrary. So, for example, if you want to improve urban mobility, which measure you take? The travel time, the speed, the pollution, the cost. So there are many things that they are related and correlated, but not necessarily are the same. In the sense that if you minimize travel time, that doesn't necessarily minimize pollution, for example. And then what you mentioned, it is true that in some cases, some technologies will be adapted faster in some places than others, but sometimes the opposite would be the case from the examples you gave, in the sense that, for example, in Kenya, in the 1990s, when the first cell phones arrived, they didn't have banks, very few branches in all the country. So they started doing phone banking with SMS like ages ago. So this is known as leapfrogging the technology. So they didn't have landlines, or they have very few landlines. Then suddenly everyone had mobile phones, and we are still bagging landlines when they're not really necessary anymore. And we are still unable to do proper online banking and, let's say, contact payments. Like also in India, they are leapfrogging technology that had to do with credit cards. So in principle, yeah, I mean, basically you have a QR code. So the equivalent here, I think Mercado Pago works something like that, but it doesn't penetrate here because we have credit cards. So the credit cards will make sure that that technology doesn't penetrate, because they charge 4% or more of commission, and these technologies will charge much less. So in India, you can go in a tuk, which is a three-wheel motorcycle like you see in Oaxaca or somewhere in Tawak as well. And they have QR code, and then with your phone, you just take a picture and you pay electronically, and it goes into their electronic wallet. So they have been already speaking. So there are experiments in Africa. Well, not experiments. It's already a company that is successful. First in Africa, delivering blood using drones, and once it was successful in Africa, they tried to take it to the United States, and it's so difficult because ancient air traffic regulations. So yeah, another example is in China, that very quickly they build a high-speed rail network all over the country. And in Europe, they are unable to do it because they already have the rail network. They have no space to build a new one, and they cannot simply stop the current one because it's used constantly. Like, okay, we will remove this line and then we'll improve it and it will be a high-speed rail. They can't do that, so they're stuck with the old technology. So in this sense, China was able to leapfrog high-speed rail. So yeah, it's kind of a very specific case by case.
I was thinking about a case in Argentina that is happening with the evaluation.
Yep.
Much of the people is starting to learn about crypto coins because they can. Well, it's better for them to see. I don't know if.
Yeah, I mean, cryptocurrencies can offer some advantages for some transactions. And for example, in El Salvador, we're seeing the experiment that now it's an official currency. From what I understand, doesn't make much of a difference overall. So yeah, some payments can be more comfortable, but it seems alternative solution like just electronic wallets are more appropriate for this type of economies. But yeah, I mean, so for example, now Russia, part of the sanction was that you cannot send money to Russia and you cannot get money from Russia, so from banks. Then you can get cryptocurrencies. And also, some people say that the problem with cryptocurrencies is that many illegal activities make the transactions with cryptocurrencies, like drugs and weapons and so on. Even when originally was supposed to be precisely to have a trace of where the money is coming from. But yeah. So from the chat, Roberto writes, could you comment on the limits of AI? For instance, so far, no AI has been able to approach rather seemingly simple tasks as a human infant acquiring language. Actually, there have been some claims of such technologies that they are equivalent to a, I don't know, 4-year-old human. But of course, these are kind of arbitrary. And this is just for language. But yeah, I mentioned at the beginning about the limits of AI. So most people will think like, okay, current AI is limited, but eventually, maybe at the end of this century, maybe even later, we will have artificial intelligence with similar capabilities of humans. And I've been thinking about this, and it's something that I have to develop better, but I would say that in principle, AI is unable to achieve that. Why? Because artificial intelligence runs on computers, and computers follow, let's say, have the same limits of formal systems. So same limits that Gödel and Turing showed in the 1930s for formal systems, in particular mathematics, I think the same still apply for artificial intelligence. And somehow they don't apply to us. So it doesn't mean that artificial intelligence will never be able to develop human level intelligence, but the way we're doing it is not sufficient. So there are two options. Because I mean, at the end, we do it somehow. So we find that's how, then we should be able to reproduce it in principle. So one might be with a different computer architecture that goes beyond those limits of formal systems. But then maybe if you do that, then you will lose some of the other requirements to have computation, formal computation. And maybe we don't have such limits because we don't need to be perfect. And we want our machines to be perfect, consistent. We don't need to be consistent. So this is related to Fitzgerald's definition of intelligence. And it's not that computers cannot handle contradictions. I mean, there's many paraconsistent logics that are able to handle contradictions. Formal systems and then include contradictions, and then you can derive the properties of such systems. The problem is that, in principle, you have so many different formal systems or different axioms to choose from. So you need like a meta formalism to decide which of the axioms is more appropriate for a specific situation. So yeah, it would be precisely in the spirit of adaptive computing. You can have like different sets of rules, or in Ashby's terms, like different behaviors of a machine. And you need to know when to switch from one behavior to the next. So let's assume that we developed an artificial intelligence and it plays chess properly. And then we have another artificial intelligence that it plays checkers properly. Then we kind of merge them, and then we need a small machine that decides, okay, which game are we playing, and decides which route we follow. And of course, we could assume that we will just keep on growing and say, okay, we will just bunch up all artificial intelligence, and you bunch them together, but then it's like an infinite progression. But somehow we managed to break away from that cycle and just make decisions naturally and adapt to the changing axioms. I mean, we don't have much problem in changing their axioms. Machines do have problems. But then you could also counter argue that we cannot change, let's say, the way our neurons or our genes work. But still we're able to solve general intelligence that computers are unable to do yet. So yeah, I mean, it's an open question. I'm right now inclined to say that there are fundamental limits to the AI we have now. We should acknowledge those limits. Let's say, on the one hand, not to expect too much from technology, and perhaps to seek ways of overcoming them. Yeah, I'm not confident we will manage to do so in terms of. Okay. So if there are no other questions, next Tuesday, and we'll see advances from your final project. So if you are here, you can just speak, and by Zoom, just tell us by Zoom.
Okay.
Okay. Have a great weekend.
Professor.
Yep.
Maybe I can talk with you from something of the